Titanium disulfide is an inorganic compound with the formula titanium 4-sulfide. A golden yellow solid with high electrical conductivity, it belongs to a group of compounds called transition metal decalcogenides, which consist of the stoichiometry Me2. Titanium 4-sulfide has been employed as a cathode material in rechargeable batteries. Structure: titanium 4-sulfide adopts a hexagonal close-packed HCP structure, analogous to cadmium iodide. In this motif, half of the octahedral holes are filled with a cation, in this case T4+. Each T-center is surrounded by 6 sulfide ligands in an octahedral structure. Each sulfide is connected to 3 T-centers, the geometry at S being pyramidal. Several metal decalcogenides adopt similar structures, but some, notably most two, do not. The layers of titanium 4-sulfide consist of covalent Ts bonds. The individual layers of titanium 4-sulfide are bound together by van der Waals forces, which are relatively weak intermolecular forces. It crystallizes in the space group P3M1. The Ts bond lengths are 2.423 A. Intercalation: the single most useful and most studied property of titanium 4-sulfide is its ability to undergo intercalation upon treatment with electropositive elements. The process is a redox reaction, illustrated in the case of lithium. Titanium 4-sulfide plus Li-2 Li-2 is generally described as Li plus titanium 4-sulfide minus. During the intercalation and deintercalation, a range of stoichiometries are produced with the general formula Lichis 2 X swells and the electrical conductivity of the material increases. Intercalation is facilitated because of the weakness of the interlayer forces as well as the susceptibility of the T/IV centers toward reduction. Intercalation can be conducted by combining a suspension of the disulfide material and a solution of the alkali metal in anhydrous ammonia. Alternatively, solid titanium 4-sulfide reacts with the alkali metal upon heating. The rigid band model, RBM, which assumes that electronic band structure does not change with intercalation, describes changes in the electronic properties upon intercalation. Deintercalation is the opposite of intercalation: the cations diffuse out from between the layers. This process is associated with recharging a Li titanium 4-sulfide battery. Intercalation and deintercalation can be monitored by cyclic voltammetry. The microstructure of the titanium disulfide greatly affects the intercalation and deintercalation kinetics. Titanium disulfide nanotubes have a higher uptake and discharge capacity than the polycrystalline structure. The higher surface area of the nanotubes is postulated to provide more binding sites for the anode ions than the polycrystalline structure. Material properties: formally containing the D0 ion T4+ and closed shell dianion S2-. Titanium 4-sulfide is essentially diamagnetic. Its magnetic susceptibility is 9 by 10⁻⁶ EMU per mole, the value being sensitive to stoichiometry. Titanium disulfide is a semimetal, meaning there is small overlap of the conduction band and valence band. High-pressure properties: the properties of titanium disulfide powder have been studied by high-pressure synchrotron X-ray diffraction (XRD) at room temperature. At ambient pressure, titanium 4-sulfide behaves as semiconductor, while at high pressures of 8 GPa the material behaves as a semimetal. At 15 GPa, the transport properties change. There is no significant change in the density of states at the Fermi level up to 20 GPa, and phase change does not occur until 20.7 GPa. A change in the structure of titanium 4-sulfide was observed at a pressure of 26.3 GPa. Although the new structure of the high-pressure phase has not been determined, the unit cell of titanium disulfide is 3.407 by 5.695 angstroms. The size of the unit cell decreased at 17.8 GPa. The decrease in unit cell size was greater than was observed for MOS2 and WS2, indicating that titanium disulfide is softer and more compressible. The compression behavior of titanium disulfide is anisotropic. The axis parallel to STS layers C-axis is more compressible than the axis perpendicular to STS layers A-axis because of weak van der Waals forces keeping S and T atoms together. At 17.8 GPa, the C-axis is compressed by 9.5% and the A-axis is compressed by 4%. The longitudinal sound velocity is 5,284 meters per second in the plane parallel to STS layers. The longitudinal sound velocity perpendicular to the layers is 4,383 meters per second. Synthesis. Titanium disulfide is prepared by the reaction of the elements around 500 degrees Celsius. T+2S titanium 4 sulfide. It can be more easily synthesized from titanium tetrachloride, but this product is typically less pure than that obtained from the elements. Titanium 4 chloride plus 2H2S titanium 4 sulfide plus 4HCl. This route has been applied to the formation of titanium 4 sulfide films by chemical vapor deposition. Thiols and organic disulfides can be employed in place of hydrogen sulfide. Chemical properties of titanium 4 sulfide. Samples of titanium 4 sulfide are unstable in air. Upon heating, the solid undergoes oxidation to titanium dioxide. Titanium 4 sulfide plus O2 titanium 4 oxide plus 2 Stis-2 is also sensitive to water. Titanium 4 sulfide plus 2H2O titanium 4 oxide plus 2H2. Upon heating, titanium 4 sulfide releases sulfur, forming the titanium 3 derivative. 2 titanium 4 sulfide titanium 3 sulfide plus S. Sol-gel synthesis. Thin films of titanium 4 sulfide have been prepared by the sol-gel process from titanium isopropoxide T(4), followed by spin coating. This method affords amorphous material that crystallized at high temperatures to hexagonal titanium 4 sulfide, which crystallization orientations in the 001, 100, and 001 directions. Because of their high surface area, such films are attractive for battery applications. Unusual morphologos of titanium 4 sulfide. More specialized morphologies, nanotubes, nanoclusters, whiskers, nanodiscs, thin films, fullerenes, are prepared by combining the standard reagents, often titanium 4 chloride, in unusual ways. For example, flower-like morphologies were obtained by treating a solution of sulfur in 1-octadecene with titanium tetrachloride. Fullerene-like materials. A form of titanium 4 sulfide with a fullerene-like structure has been prepared using the titanium 4 chloride H2S method. The resulting spherical structures have diameters between 30 and 80 nanometers. Owing to their spherical shape, these fullerenes exhibit reduced friction coefficient and wear, which may prove useful in various applications. Nanotubes. Nanotubes of titanium 4 sulfide can be synthesized using a variation of the titanium 4 chloride H2S route. According to transmission electron microscopy (TEM), these tubes have an outer diameter of 20 nanometers and an inner diameter of 10 nanometers. The average length of the nanotubes was 2 to 5 micrometers and the nanotubes were proven to be hollow. Titanium 4 sulfide nanotubes with open-ended tips are reported to store up to 2.5 weight% hydrogen at 25 C and 4 megapascals hydrogen gas pressure. Absorption and desorption rates are fast, which is an attractive for hydrogen storage. The hydrogen atoms are postulated to bind to sulfur. Nanoclusters and nanodiscs. Nanoclusters, or quantum dots of titanium 4 sulfide, have distinctive electronic and chemical properties due to quantum confinement and very large surface-to-volume ratios. Nanoclusters can be synthesized using micelle. The nanoclusters are prepared from a solution of titanium 4 chloride in tridodisylmethyl ammonium iodide (TDAI), which served as the inverse micelle structure and seeded the growth of nanoclusters in the same general reaction as nanotubes. Nucleation only occurs inside the micelle cage due to the insolubility of the charged species in the continuous medium, which is generally a low dielectric constant inert oil. Like the bulk material, nanocluster form of titanium 4 sulfide is a hexagonal layered structure. Quantum confinement creates well-separated electronic states and increases the band gap more than 1 electron volt in comparison to the bulk material. A spectroscopic comparison shows a large blue shift for the quantum dots of 0.85 electron volts. Nanodiscs of titanium-4 sulfide arise by treating titanium-4 chloride with sulfur in olelamine. Applications. The promise of titanium disulfide as a cathode material in rechargeable batteries was described in 1973 by M. Stanley Whittingham. The group 4 and V decalcogenides attracted attention for their high electrical conductivities. The originally described battery used a lithium anode and a titanium disulfide cathode. This battery had high energy density and the diffusion of lithium ions into the titanium disulfide cathode was reversible, making the battery rechargeable. Titanium disulfide was chosen because it is the lightest and cheapest chalcogenide. Titanium disulfide also has the fastest rate of lithium-ion diffusion into the crystal lattice. The main problem was degradation of the cathode after multiple recycles. This reversible intercalation process allows the battery to be rechargeable. Additionally, titanium disulfide is the lightest and the cheapest of all group 4 and V layered decalcogenides. In the 1990s, titanium disulfide was replaced by other cathode materials, manganese and cobalt oxides, in most rechargeable batteries. The use of titanium-4 sulfide cathodes remains of interest for use in solid-state lithium batteries, e.g., for hybrid electric vehicles and plug-in electric vehicles. In contrast to the all-solid-state batteries, most lithium batteries employ liquid electrolytes, which pose safety issues due to their flammability. Many different solid electrolytes have been proposed to replace these hazardous liquid electrolytes. For most solid-state batteries, high interfacial resistance lowers the reversibility of the intercalation process, shortening the life cycle. These undesirable interfacial effects are less problematic for titanium-4 sulfide. One all-solid-state lithium battery exhibited a power density of 1000 Wh/kg over 50 cycles with a maximum power density of 1500 Wh/kg. Additionally, the average capacity of the battery decreased by less than 10% over 50 cycles. Although titanium disulfide has high electrical conductivity, high energy density, and high power, its discharge voltage is relatively low compared to other lithium batteries where the cathodes have higher reduction potentials. Notes. Further reading. http://authors.library.caltech.edu/54566/1/hrst.mit.edu/rs/materials/public/titanium_disulfide.htm Dao, Y, Wu, X, Zhang, Y, Dong, L, Zhu, J, Hu, Z 2008. Surface-assisted synthesis of microscale hexagonal plates and flower-like patterns of single crystalline titanium disulfide and their field emission properties. Crystal Growth and Design. 8.8.2990-2994. doi 10.1021 per centigrams 800113N. Zhang, Y, Li, Z, Jia, H, Luo, X, Xu, J, Zhang, X, Yu, DJ 2006. Titanium-4 sulfide whisker growth by a simple chemical vapor deposition method. Journal of Crystal Growth. 293 124-127. doi 10.1016 j. jcrisgrow.2006.03.063.